We'll proceed in the commercial calculus, that is curl in calculus. Curl in calculus. What we have seen curl in calculus, as far as curling in calculus, what we have seen is if I have a algebraic vector. Algebraic vector means a vector which components of the vector is algebra. This proves that algebra is nothing but it's a function which has independent component. If I say fx equal to fx equal to f bracket x bracket close fx, do you see this is as good as any Python function, where f is the name of function and x is the parameter we are passing into. So fx equal to x square plus sin x, means algebraic equation is x square plus sin x, but this is the way it is represented. Fx equal to x square plus sin x means if there is a Python function fx, where if you pass x internally, it will do x square plus sin x on x and it will return the value. But it will have infinite value if infinite x times x different x is passed. Similar to that, if I have a vector, its component is 2i plus 3j. This is static vector. This is what we have seen. If this is x-axis, y-axis, 2i plus 3j. This is vector direction. But if it is fxi plus gx, fxi, fx comma y, fx comma yi plus gx comma yj, like x plus yi plus x into yj. Mind it, I have two components, one is I component, one is j component, and the coefficient of I component and coefficient of j component both are algebraic functions in terms of independent variable x and y. If I and j is there, x and y are independent variable and they are at both the places. So if I say I have a capital F is represented as vector field. So I have capital F as vector field equal to fxyi plus gxyj. So if that is the case, depending upon the xy value, this vector will have a variation in the position vector. If that is the case, then full arena is called vector field. If it is a static vector, then it is in one direction. But if it is a vector field where the fields are algebraic equation, then it will position vector will have more kind of reachability. If that is the case, then full is vector field. If I have a vector field, consider there is a vector field like this, and if I place an item in the vector field, what is the tendency of this vector field to rotate this item? Like if I consider the river is flowing, and this is my river. Okay, a river is flowing from left side to right side, this side to this side. So this looks like this full, this full is vector field or force of the river. Like left side to right side, river is flowing, then full left to right, full. Understandable, right? So this is left side, this is right side. River is flowing like this. If that is then full this arena, full in this direction, that is vector field. If I place an item in the river, then this item would flow along with the water. Water has force and water is making this item flow. So there is a work done by the water, that is force into displacement. Force into displacement. That is the work done by the water. What is the tendency of the water to make it rotate? So it will rotate also and it will move also. To make it rotate, that is called curl tendency of a vector field. So we are talking about curl tendency of a vector field, where a vector field has tendency to make any object rotate. Like if I carry a magnet, two magnet, one magnet here, and then there is a magnetic field If I place an iron, then it will move in one direction or this direction, whatever. What is tendency of this magnetic field to make an iron rotate on its axis also? That is curl. So we landed up in saying that curl, rather than calculating the curl, let's calculate the path independency. Path independency in the sense, when we calculate the work done by the force vector field, then work done is F, that is the force vector, capital F, that is the force vector, dot d r vector. R is the path along which force is applied. Dot. Dot means if this is the force vector field and this is the displacement I am looking from point A to point B and this is r vector, then force vector dot product of the vector dot dr vector. Dr vector, not r vector. D, integration F, capital F dot dr vector, that is integration from point A to point B. If we are displacing point A to point B, path independence comes into the picture. Whatever is the work done by the force, if this is the force, whatever is the work done by the force from point A to point B, that work done should not matter if point A and point B are connected through a line or it is connected through a semicircle, connected through a line, or it is connected through a semicircle, or it is connected to a staircase, whatever. Point A and point B only matter. Point A I know, point B I know. I know the vector field, then capital vector field dot dr vector, and then integration from point A to point B. It should be independent of the path. Path independence in the vector field. This is what we are talking. If that is the case, then what is the integration? Capital vector F, that is capital F, vector field F dot dr. Consider this integration results in algebraic equation small f. Then that will be equal to small f from A to B. Small f from A to B. If I know small f from somewhere, okay, I did the integration. If I did the integration and I got the small f from A to B, what is small f A to B? Capital F is the vector field or force field. Capital F is the vector field or force field dot d r vector, that is the path from A to B. To prove the vector field is path independent, I don't care this r vector, either it is a line, it is a circle, it is a parabola. If that is the case, then whatever the integration I am getting as a algebraic equation, that is small f, called potential function, then integration is from A to B. Small f A to B means FB minus FA. Path independence means that the potential function f, what I am getting after integration, okay, that f is only dependent upon the vector field capital F, force field capital F, not on the path. If that is the case, then integration is not required. Integration is not required if somehow I know the potential function, because I know this potential function is constant, because vector field is constant, it is not changing. Changing, what is constant? Vector field is constant, point A to point B is constant. I am calculating work done from a vector field capital F in direction of a path that is R, vector field F dot dr vector, from point A to point B. What is variable here? Vector field F is not variable. I am not talking about algebra. It is not variable here. Point A to point B is not variable. Variable is R vector. R vector, if there is point A and point B, A, B can be connected through R vector, that is a straight line. A, B can be connected through a circle, that is a circular line. It can be connected through a parabola. It can be connected through another shape. So R is variable. If this integration results in a potential function small f, and potential function is only dependent upon A to B and vector field F, then this potential function, then this vector field is called path independent, because it is not dependent upon R vector. So I take any r vector. If I take a straight line as r, since it is not dependent upon it, I take the simplest r vector, that is the straight line, and I calculate the integration, and then I get the small f, that is potential function. Now potential function from A to B. Now I know since it is path independent, I go with the circle, I go with, anyone would ask what is the force, what is the force, what is the work done by a force vector field along the path A to B, where A to B are connected as a circle. If I know this force field is path independent, then I can calculate through a straight line also, because it's independent of the path, and calculating the integration is far easy with the straight line. Now I calculate and get the potential function, and since it is dependent upon point A and B, in the potential function I can simply say FB minus FA, where F is small, potential function small. So for a particular vector field, if I get a potential function of small f, I know vector field is path independent, then irrespective of any path, I just need to place fb minus fa, where f is potential function small f, path independent. So if someone is saying that if I have this vector field, what is work done from point A to point B, any point A to point B? If I somehow prove this vector field is path independent, then I have to find algebraic function, potential function small f, which is dependent upon the vector field itself. Or I can try with a simple straight line connecting A and B. Once I get the potential function small f, then story is done. Beyond that, I just need to set FB minus FA to get the net work done. If it is A to A, then certainly it is FA minus FA is 0. Now, rather than calculating the full path in the path line integral, capital F vector dot dr vector is also called line integral. Means if this is the vector field and this is the path from A to B and this is vector field, then what is line integral? The line integral of this vector field, line integral means vector field f multiplied by the line dot product. So this is work done by this vector field f, that is in this line. In this line means if this is a vector field, consider this is a force field and there are 2 points, point A and point B. If I keep a mass at point A and point A and B are connected through a semicircle, then this mass would travel from point A to point B because of this vector field, because a force vector field. Then how much work is done? That is force vector field multiplied by this distance with dot product. That is the work done. Capital F dot dr vector. That is the why d came into the picture, because of algebra. If it is a static vector force field, that is 2i plus 3j, and this path is also static, no algebra is there, then certainly capital F dot r vector, F vector dot r vector will also work as far as work done is concerned. But vector field F is algebraic function, this path is algebraic path, then capital F dot dr vector. So what is the work done? What is the work done by this capital vector field? Bringing one mass from point A to point B in circular path. If it is path independence, then circular path doesn't matter. What is the work done of this force? Bringing a mass from point A to point B, either it is a straight line or circular line, whatever it is, the work done will be same. If that work done through one path is small f, small f, that is also called potential function, setting the limit in the potential function from A to B, then FB minus FA, small f, it gives me the line integral or work done. Then I don't need anything else. If someone asks me that what is the work done from point alpha to beta, when vector field is capital F, I know the potential function through one calculation, and after that I just need to set alpha to beta. F beta minus F alpha, because it is path independent. If it is path independent, then potential function will come same for whatever path dr I take. But how I prove it is path independent? One way we have seen that I take a generic path. If it is path independent, if this integration capital F vector dot dr vector, if this integration is path independent, capital F vector dot dr vector, if full integration is path independent, then I can take a generic path. Generic path is if this is a point A and this is point B, I take any path in between. That path, any point on that path can be represented as coordinate x comma y. If that is the case, then that is xi plus yj position vector. Then I have capital F dot d of xi plus yj. That will become capital F vector dot dxi plus dyj vector. Capital F vector, since it is a vector, it has f1i plus f2j as component. So net integration becomes f1 dx, f1 dx dot product, so ij gone, plus f2 dy. So f1 dx plus f2 dy is the integration. f1 dx plus f2 dy is integration. If this integration results in a potential function small f, then it is as good as the gradient of this small f, the I component df by dx, d small f by dx would be f1. d small f by dy would be f2. That's why f1 dx plus f2 dy is small f. If that is the case, so this if the, we have taken generic case. This proves that if I find a small f potential function, if I find a small f potential function for which gradient vector is vector field, then it is done. Reverse way, if I have a potential, if I have a vector field capital F, and if I calculate the integration of capital F component wise, f1 dx plus f2 dy, this is for any generic path, we consider it as path independent. If I calculate this integration and it results in small f, that is potential function, then a small f df by dx would be f1. Makes sense, right? And df by dy would be f2. So df by dxi plus df by dyj is called gradient vector for potential function small f. That gradient vector is exactly equal to capital F vector field. If that is the case, if we are able to find a potential function for which gradient is vector field capital F, then it is path independent, because we started with the path independence way, then only it would happen. Anyone would say, I will find a potential function for which the gradient vector is capital F. No, not possible. We have last video, we showed it, it is not possible. If vector field is x plus yi, then you cannot find a potential function small f for which gradient vector is x plus ij, x plus yi, not possible. So for all vector field, finding a gradient vector, finding a potential function whose gradient vector is the vector field is not possible. Like x plus yi is the vector field for which gradient vector, for which potential function we cannot find. What is the other proof? Other proof, what we are trying to show? We are trying to show is path independence. Path independence, consider a simple calculus. F, okay, I have integration from a to b of a function that is gradient of f in 2D plane. 2D means there is one independent variable, that is x-axis. There is one independent variable, that is x-axis. That's it. So I have the integration will be dx only. If there is one independent variable x-axis, then integration is one independent variable, means one line only. One line. That is I vector or x-axis. If I have a function f, then gradient of function f, that is df by dx into dx, integration from point A to B, isn't it fb minus fa? df by dx is nothing but a function that is gradient of f. Gradient of f along x-axis is df by dx. So gradient of f df by dx, df by dx, or the derivative of f, integrating derivative of f with dx from a to b, isn't it equal to f, simple f, df by dx into dx, integrating df by dx with dx from point a to b is same as f limit a to b, that is fb minus fa. Makes sense, right? fb minus fa. If that is the case, then the value, okay, now if I calculate gradient of f df by dx into dx from point a to b, if this is x-axis, then point a to b, and integrating the derivative of f with dx results in f1. Df by dx from a to b is f limit a to b, fb minus fa. That is the case. What? So in single dimension, we can say that fb minus fa, f is a function, fb minus fa, f bracket b bracket close minus f bracket a bracket close, fb minus fa equal to integration from a to b of gradient of f along dx. This is single dimension. Can I move forward and convert into 3D? 3D now, we have two independent components. This is xy plane. One is x-axis, one is y-axis. Two independent components. If there are two independent components and there is a surface, then there are many vector possible here. This is I vector, this is j vector, this is any r vector from the origin. There can be many r. If this r is like this, then this becomes x-axis. If this r goes like this, then if r moves like this, then it becomes y-axis. If r moves like this, then it is any r. But if r moves like this, it becomes x-axis. But it is not the case in the 2D. There is a fixed x-axis. It cannot move like this. But in 3D, where we have xy plane and z is vertical, fxy, then I can have any r vector on the xy plane. Okay, if that is the case, can I extend fb minus fa equal to integration from point a to b? Now a is x comma y. Earlier a was x1. Now a is x comma y, b is x comma y. So fb minus fa equal to small f equal to from point A to B gradient of f dx. This is what we said in the 2D. Now dx, x-axis becomes any r vector. So dr. So from point A to B gradient of f dr is nothing but fb minus fa. But idea is, can we really calculate f gradient of f in xy plane dr? Okay. Now if I go with the differentiation, if I go with the derivative of function f, what we are trying to say, Cap? Derivative of function f dr means derivative of function f along r vector. If it was df by, if derivative of f along dx in 2D we showed, right, from point A to B integration of derivative of f along x-axis is fa minus fb. Now it is derivative of f along any axis, that is r vector. So derivative of f dr from A to B. This is directional derivative of a function along vector r. If I trying to calculate derivative of f along r direction, r is a line, then it is a directional derivative of vector f of function f along the vector r. Same, right? If I say gradient or derivative of f along r is any vector on xy plane. If that is the case, then directional derivative of function f along any r vector is nothing but gradient of f dot unit vector along r vector dr. So unit vector, understandable. I am trying to extend the 2D concept. So if I am trying to extend 2D concept, that is fb minus fa equal to integration from point A to B derivative of f along x-axis dx. Now if I am extending it to 3D, where instead of x-axis I have xy plane, then fb minus fa equal to point A to B and derivative of f along any r line dr. Derivative of f along any r is directional derivative of f along r vector. That is gradient of function f, gradient vector of function f dot. This is what we have seen in the past. Gradient of vector f dot gradient of vector f dot any unit vector in r direction. Gradient of vector f dot unit vector along the r direction dr. This unit vector, if I place inside dr, then r becomes r vector. Earlier it was dr, small r. Dr means small r. Now when unit vector goes inside it, that is along the r line, then it becomes dr vector. So fb minus fa, small fb minus fa equal to integration from A to B and gradient of f dot dr vector. Isn't it same as what is difference between small f? We are talking about if I go with the line, if I go with the line integral of a vector field capital F, if capital F is a vector field for which line integral is capital F dot dr r vector integration from A to B, that is the potential function small f from A to B, fb minus fa. Isn't it same? Okay, if I am going with calculus, then then integration from A to B, gradient of function f dot dr vector equal to the potential function f, that is fb minus fa. If that is true, then gradient of f I can replace with vector field. So if vector field, if vector field is gradient of f, then it is path independent in a way that net result is fb minus fa. Doesn't depend upon anything else. Vector field f, if vector field capital F is gradient of f, then this through calculus, then it is as good as gradient vector potential function f b minus fa. Okay, probably we will talk more on this. This is another proof from right hand side. We started one proof, that is path independent, where we took path as xi plus yj vector, and we proved that if I find a potential function for which gradient vector is vector field f, or capital vector or vector field, if I do integration of vector field f with dx and dy and it results in potential function other way, then it is path independent because net result is fb minus fa. Here we started from other side. If net result is fb minus fa, if I take that as source, fb minus fa, whatever I am calculating, it should be dependent upon b and a only, fb minus fa. Then it is nothing but gradient vector of f dot dr vector, where we started with the line integral is capital F dot dr vector. From here it is gradient of a small f dot dr vector. This proves that line independence is possible when vector field capital F equal to gradient of small f. We will proceed on it.